Hi, today we're going to be talking about formulas. Now, basically, the information that I'm going to be giving you is ultimately we're going to be trying to get from percent compositions back to the chemical formulas. Now, there are two main types of chemical formulas. There's empirical formulas and there are molecular formulas. And we're going to look at the differences between the two. Now, empirical formulas are the simplest whole number ratios of the atoms present in a compound. All right. So if you, it may not necessarily be the chemical formula of that particular compound, but if you took all of the subscripts and reduced them down to the lowest possible whole number ratio, that would be an empirical formula. So by definition, the chemical formulas for ionic compounds are empirical formulas. Because remember, when you're writing the chemical formula for an ionic compound, it is always, cross, drop, and reduce. So you always want to reduce it down to the lowest possible whole number ratio. All right. And the mathematical process I'm going to be showing you is how to take and find the empirical formula from the percent composition of the compound. So first we're going to talk about it. Then I'm going to show you a sample problem. And then I'm going to talk about molecular compounds. And then I'll show you a sample problem with how to find those from the empirical. All right. So how to calculate the empirical formula. Step one, obtain the mass of each element present. Now, sometimes the problems are going to get that you're going to see will tell you in a particular sample there are 17 grams of element X and 42.3 grams of element Y. So if they already give it to you in grams, that's simple. You just move on. But sometimes they give you the information as percentages. Like in a percent composition, they might say that there is 17% of element X and I don't know, 83% of element Y. Well, if that's the case, then just pretend that you have 100 grams of the substance. And if you have 17% of one element, that means you have 17 grams. And then if you have 83% of the other element, boom, you have 83 grams. So if it's given percents, to simply change the percent to grams. Step two, use the molar mass to convert each mass into moles. Just like you would do with a normal chemical conversion, you take the mass in grams and basically divide by the molar mass. Then the last step, this is the trickiest, you want to divide the number of moles, all right, because you now have moles for each element, the number of moles of each element by the smallest number of moles to convert the smallest number to 1. So let's say you do all of these divisions and come up with the number of moles of element X and the number of moles of element Y. Whichever one of those is smaller, divide each of them by that lesser number. All right. And then you want to basically round off to the closest whole number. Now, if you do it correctly, especially in this class, the formulas that are always going to give you very simple ratios. Sometimes when you divide, you're going to get a number that is like 3.5 or 2.5. In that case, then you're going to have to round up. Okay. So if they're whole numbers, use those numbers as the subscripts for the empirical formula. If one or more are not whole numbers, then proceed to step 4 by scaling up to whole numbers. You simply multiply all of them from step 3 by the smallest whole number, and that will convert all of them to whole numbers. For example, let's say you find that when you divide by the smallest number of moles, you get 2.5, and then the smallest whole number would be, let's say, 2.5 and 1. Okay. So how do you get 2.5 to be a whole number? Well, 2.5 is if it's 0.5, that means it's a half. So if you take 2.5 and you multiply it by 2, you get 5. So if you do that, you have to multiply the other subscript by 2 as well. So you end up with 5 and 2. I know it's confusing. Don't worry, I have a good sample problem here to show you for that. All right?
Hi, this problem is to help you with calculating empirical formulas from percent composition. Either they give you the mass of each element present, or they give you the percent composition. If it's the percent composition, there's one small extra step, but basically you take the percentages of each element and change them, and you basically pretend that you have 100 grams of it, and you change it into you change it into grams. So if we have 65.02%, that becomes 65.02 grams of platinum. And we have 9.34 grams of nitrogen, 2.02 grams of hydrogen, and 23.63 grams of chlorine. Now, once we have that, our first step is to change them into moles, okay? We want to convert all of these into moles. And the way we go from grams into moles is by dividing by the molar mass of each element. So we use our periodic table. We set up a little grid, and we know that for every 1 mole of PT, platinum, according to our periodic table, the molar mass of PT is 195.08. So that's 195.08 equals. On my calculator, I go 65.02 divided by 195.08, and I get 0.3333. Since this has 4 significant figures, I want to have that go out to 4 sig figs as well. And that's moles of platinum. And I do the same thing with each of the other elements. To get from grams of nitrogen to moles of nitrogen, I know that for every 1 mole of nitrogen, there are 14.01 grams. So I go 9.34 divided by 14.01 equals, and I get 0.6667 moles of nitrogen. I do the same thing for hydrogen. That's 1 mole of H for every 1.01 grams of H. And I end up getting basically 1 mole of hydrogen. Technically, it should be 1.000 moles of hydrogen. And then for chlorine, for every 1 mole of chlorine, there are 35.45 grams of chlorine. And according to my calculator, 23.63 divided by 35.45, and I get 0.6666 moles of Cl. Now, the next step is I look at all of these values and I divide all of them by the smallest number. All right, and since the smallest number amongst all of these is right here, for the platinum, I divide everything by 0.3333. 0.3333, 0.3333, 0.3333. Now, when I divide, I want to round off to the nearest whole or half number. All right? And basically, we're trying to figure out what the ratio is, but we want them all to be whole numbers. So this, I divide by the same number, I'm going to get 1 platinum. Here, I divide 0.6 divided by 0.3, rounded off. I'm going to get 2, and that's going to be nitrogens. Here, 1 divided by 0.3, that comes out to be 3 hydrogens. And then 0.666 divided by 0.3333, equals 2 chlorines. Now, these numbers, all right, these numbers are going to become the subscripts. Now, if they weren't whole numbers already, if you rounded off and it became, it was like 1.3 or 1.6 or 1.5, you then do the process again, simply dividing by the lowest number of these now until you end up with a whole number. Okay, so until you end up with all of them being whole numbers. But these end up being the subscripts. So I have PT1, N2, H3, Cl2. And that is the empirical formula for this compound. I hope you found this useful.
So we're going to go through this problem. And also, now that you know how to do empirical formulas for normal compounds, you guys are also going to have to know how to do empirical formulas of hydrates. All right. So this is a little bit trickier, but in a way it's a little bit easier. Now remember, a hydrate is an ionic compound that can have water molecules trapped within the crystal matrix. Sorry about that. So let's say you have, this is the crystal matrix of an ionic compound. You can have water molecules are actually inserted into the crystal matrix and are in between the in between the ions. And what this does is that this causes the crystal to actually expand. If you've ever had a crystal growing kit or seen one of those where grow your own crystals, or if you ever had basically something like that, where you just add water and let it sit for a while, that's what's going on here. You can take a powdered ionic compound, add a little bit of water, and boom, they will grow into a larger size. Now, the cool thing about that is you can then take that crystal, heat it up, and get rid of the water and make it go back down again. Now, the formulas for hydrates always take a certain form. They always look like something like this. So if you have copper 2 sulfate pentahydrate. So we have the copper 2 sulfate here. Now the pentahydrate, it uses the Greek prefix, just like you did for the molecular compounds. All right, remember when you had the name molecular compounds? When you had to go through and use the Greek prefixes for, like, 1 was mono, 2 was di, things like that. Well, here, if you see that Greek prefix in front of the word hydrate, that indicates how many waters there are for every one formula unit of the ion. So in this case, imagine, if you will, let's say here's copper and this is the sulfate ion, SO4. You would have, since it's a pentahydrate, you would have like 5 water molecules for every pair of copper sulfate. All right? And that's why it's a pentahydrate. Well, the procedure I'm about to show you will show you how do you figure out what this formula is if you know, like, the percentage of the compound that's water. All right? So when calculating empirical formulas, the trick is treat water as if it were a single element. In other words, don't separate them into hydrogen and oxygen. And you can go from, hey, you have this compound of this hydrate of copper 2 sulfate, and it's, 36% water. What is its empirical formula? And that's the sort of problem that I'm going to show you now. You need to know how to do this, so when we do the lab water of hydration, then we're going to be using this process in that lab. So make sure you pay very close attention.
Now, this is how you do empirical formula problems for hydrates, all right? Compounds that are hydrates. Now, so we're looking at this, and first of all, we want to make sure we have the correct chemical formula for copper 2 sulfate. So real fast, I know that copper 2 is 2 plus, sulfate is SO4 2 minus. That's a 1-to-1 ratio, so that's going to be CuSO4. Now, we know, the one thing that we know is that it is 36.48% water. All right, and that's going to be a certain number of H2Os. And what we're trying to find is what is the empirical formula for a hydrate of this, and we want to find out how many waters there are. So the way we go about doing that is realizing, well, if we have 36.48% water, that means the rest of it is copper 2 sulfate. So we simply take 100 and minus 36.48, all right, 36.48, and we find out what is the percentage that is copper 2 sulfate, and we find that that's 63.52%. All right, now we keep these together as compounds. So we know that we have 36.48% water, 63.52% copper 2 sulfate. So we have CuSO4 and we have H2O. Now the CuSO4, we're going to change these, remember, into grams. So we know we have 63.52 grams of that. Okay. And for the water, we have 36.48 grams. Now we need to then convert them into moles, just like before. Now we need to have the molar mass of CuSO4. So off to the side here, actually I'm going to go over here, I know I have one copper at 63.55. I have a sulfur, which is 32.07. And I have 4 oxygens, each one is 16, so 4 of them are 64. I add it all up, 32.07 and 63.55. I get a molar mass of 159.62. So I know that 1 mole of CuSO4 is equal to 159.62 grams. So I take 63.52 divided by 159.62, and I see that that is 0.3979 moles of CuSO4. I do the same thing for water. Water's molar mass is 18.02 grams for every 1 mole. All right, and that's CuSO4, that's H2O, So I get 36.48 divided by 18.02, and I get 2.024, excuse me. All right, and that's moles of CuSO4. Now I do the same thing that I did before, and I divide by the number of moles that is the lowest. So I'm going to divide each one by 0.3979. 0.3979. That's obviously going to be 1, but on my calculator, when I take 2.024 divided by 0.3979, I get 5.08785, so forth and so on. And I round that off to the nearest whole number. All right, so you can see how I have that. It's going to round off to the nearest whole number, which will be 5. So for every 1 CuSO4, I have 5 H2Os. And that equates out to CuSO4 dot 5 H2O. And that is the empirical formula for a hydrate. I hope that was useful.
Now, the last thing is, now that you know how to calculate empirical formulas, that works great. If you're dealing with an ionic compound, that's all you have to worry about, all right? Because the chemical formulas of ionic compounds are empirical formulas. But what if you're dealing with, a excuse me, what if you are dealing with a molecular compound, all right, something that's a molecule? See, the problem with molecular compounds is that they use molecular formulas. Now, molecular formula is the exact formula of the molecules present in a substance, all right? Now, the problem with that is that you can have more than one molecular formula might have exactly the same empirical formula. For example, let's see, can I? No, it's not going to let me write on here. So let me do this. Let's say you have the formula CH2O. All right, you have CH2O. Now, this is an empirical formula. All right, because if you notice the subscripts, you cannot reduce down to any smaller numbers. However, if you are doing an analysis of a compound and you get back that from the percentages of carbon, hydrogen, and oxygen, that it is, one carbon for every two hydrogens for every one oxygen, that's all well and good, except there are more than one compound, molecular compound, that has this empirical formula. Just to name a couple, you could have all of these. All right, all of these molecules have exactly the same empirical formula. All right, if you reduce these down, like this right here is formaldehyde. All right, formaldehyde is an element, a compound that was used a lot in the embalming of bodies and the preservation of organic material. As it turns out, it's cancerous, so we don't use it anymore. But back in the day, if you had, let's say, a frog to dissect, or if you wanted to keep a body part from decaying, you would embalm it in formaldehyde, and that's this formula. But this stuff right here, this is acetic acid. All right. Whoops. It's actually supposed to be C3H6O3. This is acetic acid. This is the same stuff. Actually, sorry. I was wondering why I was doing it wrong. C4, there we go. C2H4O2. This is acetic acid. This is basically vinegar. But if you notice, if I reduce the 242 down to the lowest whole numbers, I'm going to get formaldehyde again, aren't I? So these two both have the same empirical formula. And then finally, you have this guy here. This is glucose. It's a type of sugar. And if this one, you reduce it by dividing each by 6, again, you get one carbon, two hydrogens, and one oxygen. All three of these have the same empirical formula. So if all you have is the empirical formula and you're dealing with a molecular compound, then you don't know exactly what you're dealing with. All right? Therefore, there's one more step, one more mathematical step to take an empirical formula and go to the molecular formula. All right? And you need two things. One, you need the empirical formula, and you also need to know the molar mass. All right? So I'm going to show you now how to do this process using this sample problem.
Hi, this sample problem video is to try and help you figure out how to what the molecular formula for a compound is from its empirical formula. And the two things that you need to start off with is the empirical formula and the molar mass of the actual molecular formula. So what you do is, first step is you figure out what is the molar mass of the empirical formula. So we have carbon, hydrogen, and oxygen. We have one of those, two of those, and one of those. We multiply by the molar masses, and we get 12.01, 2.02, and we get 16. You add it up, and you get 30.03 grams. Now, the next step is you take the mass of the overall compound, in this case, it's 180 grams, and then you divide it by the molar mass of the empirical formula. And when I do that, and I round it off to the nearest whole number, and I get 6. Now, that 6 represents what we multiply all of the subscripts of the empirical formula by. Because remember, the molecular formula is always going to be a whole number multiple of the empirical formula. So remember, the empirical formula is the lowest common ratio of each element to each other. And the molecular formula is simply the formula of one molecule of that compound. So I take the 6 and I multiply and distribute that into each of the subscripts. And I get C6H12O6. And that is the molecular formula of this compound. I hope you found that useful.